Sweet. So now, for the last part of our 3 easy pieces, we're going to challenge ourselves and try to find a Laplace transform of t minus t naught times e to the negative alpha t minus t naught times the step function t minus t naught. So when faced with complicated functions like this, you first want to be able to identify the main operations in f of t. So that means we first see 3 time shift terms. We also see an exponential time decay term, and there seems like a t multiplication term, and finally we have a step function term. So once you've identified all these properties, you should use the online Laplace transform tables to stock up your toolbox. So here we go, the 2 domains in question, where g of t usually transforms to g of s. Now a time shift in the time domain will usually correspond to a phase shift in the s domain. Now exponential time decay in the time domain will usually correspond to an s shift in the s domain. Now here's something new. A negative t multiplication in the time domain actually corresponds to a differentiation in the s domain. That's kind of cool. So last but not least, we have the step function, u of t transformed to 1 over s. Okay, so we're going to strategize by learning how to cascade these identities on top of each other. So the main strategy is the following. We're going to try to use the peel the onion approach to solving those problems. So what do I mean by that? That means supposedly you have a time domain function f of t where it has many mathematical layers on top of each other. And what you want to do is peel the onion, which means really you want to remove the topmost math operation off. Hence you're going to get a smaller function or a smaller onion. So you keep peeling mathematical functions off until you get to the core of the onion, which means the function g of t, which you can't strip down any further. So then you find the Laplace transform in the s domain, and then in the s domain you back reconstruct the math operations that you deleted so that you reconstruct the onion in the s domain. And that means you're going to have a Laplace transform pair, which will be your final answer to the problem. Okay, so what we're going to do is we're going to cookie cut out our Laplace transforms table, paste it onto a new page, and then we're going to move the paper to the left a little bit, and let's start. So we're going to keep track of 3 things. We're going to have the time domain expression, we're going to have a picture of the time domain, and we're going to have the s domain expression. So let's write down f of t. It's going to be t minus t naught, e to the negative alpha t minus t naught, times the step function t minus t naught. So f of t looks something like this. So if we have a delayed step function right there, so anything prior to t naught, nothing happens. Now, after t naught, we're going to have 2 time shifted terms. So that means whatever I'm going to draw here should be a time shifted version of t times e to the negative alpha t, which looks like that. Okay, so it's time to peel the onion. So first what I want to ask is, what if we remove all time shifts from f of t? So that means every instance of t minus t naught, I'm going to write t like this and like this. So there you go. So what does a picture of this function look like? Well, you still have the step function, which means nothing happens prior to 0. And now we just have t times e to the negative alpha t, the unshifted version. Okay, so let's peel the onion some more. Let's suppose we get rid of the exponential time decay term. So that means we're going to get t times u of t. So what does that look like? Well, nothing happens prior to t equals 0. And then we get an escalator with a function t. So that means it's a ramp function, right? Cool. Last but not least, we have a t multiplication that we would like to get rid of. And when we do, we're just going to get u of t, which is the step function. Oh, score, man. And you know what really happened? We've actually reached the core of the onion, right? U of t is as simple as it gets. So in fact, we're going to draw the core right there, just for kicks. Okay, so now we know the function u of t is shaped like a step function at t equals 0. And what's the Laplace transform of this guy? We know this. This is just 1 over s. So now we're ready to reconstruct the onion in the s domain. So to do that, we first, if we have removed a t multiplication, we're going to add that back in the S domain. So let's take a look at our table. So a negative t multiplication corresponds to a differentiation in S domain. So we're going to carry that negative sign over to the right hand side. And that means to add the t multiplication back, we actually need a minus differentiation in the S domain. So we're going to differentiate 1 over s and then add a negative sign. Then we're going to get a plus 1 over s squared. Aren't these Laplace transform pairs of each other? Yes! This is too cool, right? Okay, so now we're going to add back an exponential time decay. And for our table, we see that a time decay term causes a s shift in the S domain. So that means we need an operation here where we're going to add an s shift by a plus alpha in the S domain. So that means we're going to get 1 over s plus alpha squared for this answer. And similarly, I wonder if these are Laplace transform pairs of each other. And you know what? They are. Excellent. And finally, we're going to add back the time shift in the S domain. To do that, we say that a time shift corresponds to a phase shift in the S domain. So that means we're going to take our expression and we're going to now add a phase shift term on top of that 1 over s plus alpha squared term. And that means we're going to get a final answer of 1 over s plus alpha squared times e to the minus st naught. So that is actually f of s, which is the Laplace transform of f of t. Awesome.